Okay, hello everyone. We are finishing up 6.5 today. So, first thing we're going to do is talk about the polar equation of a limacon. Okay, limacon with that little squiggly there. Can you guys see? Yeah, you can see. Okay, so we have R equals A plus minus B cosine theta. And we're going to make a little table here. R equals A plus minus B sine of theta. Okay. So if it's positive, so if it's A plus B cosine theta or A plus B sine theta, then this opens to the right, and this one opens to the up, okay? Cosine, x values left and right. I know we're not using x and y values, we're in polar coordinates, but kind of the same deal. Okay, same thing with sine, up and down. Okay. If it's negative, so a minus b, then this one opens left, this one opens down, okay, and then the furthest intercept. So the furthest intercept, if it's positive, then your furthest intercept here is absolute value of A plus absolute value of B, comma 0, because it opens to the right, and that's 0 degrees to the right. Whereas here, it's absolute value of A plus absolute value of B, comma pi over 2, because it opens up, and pi over 2 is straight up. If it's negative, then it's absolute value of A plus absolute value of B, comma pi for the cosine, because it opens left and pi is left. And absolute value of A plus absolute value of B, comma 3 pi over 2. Because it opens down, and 3 pi over 2 is down. Okay. Now, to show you the pictures of these, so I'm going to erase this now. Just had a bad feeling that it wasn't going. No, it's going. Okay. So limacons are kind of egg-shaped. They're not ellipses, they're not circles, they're egg-shaped. And they can be less egg-shaped depending on the numbers we use for A and B, but they're egg-shaped. So kind of looks like that a little bit. Okay. So if absolute value of A over absolute value of B is greater than or equal to 2, we get this shape. We get a dimple. So it kind of looks like this. Well, these are the same length, so it should be kind of like that more. We get this little dimple here when the absolute value of A over B is between 1 and 2. Okay, and the dimple is the absolute value of A minus the absolute value of B long. So how far do we dimple? Absolute value of A minus absolute value of B. Okay. When the absolute value of A over B is equal to 1, that's where we get something called a cardioid. We call it a cardioid because it looks like a heart. The dimple is so far in that it actually touches the pole, so 0, 0. So it looks something like this. Okay. Notice all of these, they're kind of opening up or looking, like opening to the right. So this is the A plus B cosine theta. But you would just rotate them according to if it was sine, cosine, positive or negative. And then if the absolute value of A over B is less than 1, once again sorry, my screen just went black. We're still recording, good. The dimple is so long that it actually loops back on itself. So it looks like this. It looks something like that. Okay. And that loop, the loop is absolute value B minus absolute value of A long. Okay. And then to figure out where they intersect on the perpendicular axis, so like right there, so the intercepts of perpendicular axis is plus minus A. Okay, so like that point right there, see this is the perpendicular axis to the one it's opening up on. That point right there, that's just plus minus A. Okay. So an example, so this is example 2. We want to graph r equals 2 minus 2 sine of theta. So we're using sine, so it's going to open up or down. It's minus in the middle, so it opens down. Opens down. The furthest intercept, so that's the absolute value of A, so 2, plus absolute value of B, which is 2, comma 3 pi over 2, because it opens down. So we get 4 comma 3 pi over 2. And then absolute value of A over B is absolute value of 2 over 2, so 1. That means it's a cardioid. Okay, so our graph, oh, there's the bell for lunch. See, I'm working through lunch for you guys. Yeah, you're welcome. So let's see here. So we have a furthest intercept at 4 comma 3 pi over 2, so that's down here. It's a cardioid, so we know it's going to intercept a pole. A is 2, so the intercepts of the perpendicular axis are at 2. So 1, 2, 1, 2. And so it's going to look something like that. Okay. All right. Now let's talk about rose curves. Rose curve is a bad name. They don't really look like roses, they look like daisies. But I guess daisy curves doesn't sound as cool. So, rose curves. So we have two equations. R equals A cosine n theta, and R equals A sine n theta. Okay. So when n is even, we have 2n petals. Okay, which kind of makes sense, right? 2n makes an even number. Okay. When n is odd, we have n petals. And the length of each petal, is A. Okay. So let's look at the 2n petals circumstance. For the sine function, the petals are in the quadrants, and there's n over 2 petals in each quadrant. Okay. For the cosine function, So instead of having petals in each quadrant, it has petals on each axis. And then there can be extra petals in between here if n is big enough. And how you figure that out is n minus 2 over 2. So there are n minus 2 over 2 petals in each quadrant. Okay. Now for if we have an odd number, so if n is an odd number, meaning n petals, for cosine, we get something that looks like this. It's symmetric over theta equals 0. For sine, there's two different things. We get something that looks like this. So a petal is on 3 pi over 2. Something like that. If n is 4k minus 1, meaning if I can write n as 4k minus 1 where k is a natural number. Okay, and I'll do an example. And then if n is 4k plus 1, then it's symmetric over the pi over 2. All right, so this is symmetric over 3 pi over 2, and this is symmetric over pi over 2. Okay. So an example. Example 3. R equals 2 sine 3 theta. Well, n is odd, right? It's 3. N is odd. That means there are 3 petals, right? N petals. It's sine. Okay, so we're going to use the sine version. Notice that 3 equals 4k minus 1 when k equals 1. Right? So that's what I mean by the 4k minus 1. If I can plug in a natural number, 1, 2, 3, 4, 5, so on and so forth, into k and get n out, that's when I use 4k minus 1. I can't use 4k plus 1 because I can't get 3 out when I do 4k plus 1. If I plug in 1 for k, I get 5, not 3. Right? So because of that, we know that our graph is going to be symmetric to pi over 3, or 3 pi over 2, excuse me. And there's 3 petals, so you just need 2 more, and they got to be symmetric to that 3 pi over 2. And remember, our petals are a long, so 2 long. So this is 2. I guess this should be a little bit longer, right, to make it 2. This should be a little bit longer to make it 2. And there's your graph. Now, if I were in class, we'd get on Desmos and we'd play around with this stuff to notice patterns and things like that. I would recommend, let's see, this video's right now 14 minutes long. We probably only need another 10 minutes, excuse me, for the rest of this. So you're gonna have a video that's like 25 minutes long. You have an 87-minute class period. You guys, help each other out. You're doing this stuff, like teach each other, but also get on Desmos, play around with some of these graphs. Okay, just type these graphs in. You can actually just use R's and thetas on Desmos. You can actually, if you go to the upper right-hand corner of your Desmos calculator, graphing calculator, there's like a little gear settings. You can change it to polar coordinates, so the circular plane, and graph these, and change n to 4, 5, 6. Change sign, change these numbers, and you'll start noticing the patterns and where I'm getting these patterns from. Okay, now we're switching gears and we're going to convert between polar and Cartesian. Okay, or rectangular. So conversion between polar and rectangular. Okay, so a couple definitions here for you. So x equals r cosine of theta. We get that just because the definition of cosine is x over r, and we multiply both sides by r to get x by itself. Similarly, y equals r sine theta, right? Sine is equal to y over r, multiply both sides by r, you get sine by itself. Then we have r is equal to the square root of x squared plus y squared. That's just Pythagorean theorem, okay? And then Pythagorean theorem, and then theta is equal to tangent inverse of y over x. And that comes from the definition of tangent. Tangent theta is y over x, inverse tangent both sides, and you get theta equals tangent inverse of y over x. Oops. Okay. So 4 more examples and we're done. Example 4. So we want to convert the point 6 comma 3 pi over 2, or 3 pi over 4. So notice 6 comma 3 pi over 4 is polar coordinate because it has an angle. So we want to get it to x and y's. We want to get an x comma y. So we know that x is equal to r cosine of theta. So 6 times the cosine of 3 pi over 4, which is 6 times cosine of 3 pi over 4 is negative square root 2 over 2. So we get negative 3 square root 2. And then y is equal to r sine of theta, which equals 6 sine of 3 pi over 4, which is 6 times square root 2 over 2, positive, which equals 3 square root 2. So we get negative 3 square root 2 comma 3 square root 2. And there's our rectangular coordinate. Okay, example 5. Convert the point negative 2 comma negative 2 square root 3. So notice this time there's no angle, so it's not polar coordinate, it's rectangular, so we're going to convert to polar. Well, we know that r is equal to the square root of x squared plus y squared. Right, this is r and theta. We want, or sorry, this is x and y. We want r and theta. Well, that means r is equal to the square root of negative 2 squared plus negative 2 square root 3 quantity squared. So that's the square root of 4 plus 12, which is the square root of 16, which is 4. So that's r. And then theta equals tangent inverse of y over x. So that's tangent inverse of negative 2 square root 3 over negative 2, which is tangent inverse of square root 3. So we got to ask ourselves, what angle, when you take its tangent, gives you square root 3? Well, that's pi over 3 and 4 pi over 3. So which one do we use? Well, let's look at where this point is, the xy point, the rectangular point. We're at negatives, negative x and negative y, so it's down here somewhere. Well, that means that we want to use the angle in quadrant 3, so 4 pi over 3. So our point is 4 comma 4 pi over 3. And there's your answer. Oh man, you guys realize that today is, for Teacher Appreciation Week, today is go get a free massage. And I'm doing this for you instead of doing that. Yeah, you're welcome. Okay, example 6. Let's see here. We're on good now. So now we're going to convert equations. So example 6. We want to convert r squared cosine 2 theta equals 3. We want to convert that to rectangular. So we want x's and y's. Now notice, we have a cosine of 2 theta, but our definitions only have theta. So, yes, Adam, you're right. We need to use an identity. So, we can write this as r squared times 1 minus 2 sine squared of theta equals 3. Distribute the r squared minus 2 sine squared theta, or 2r squared sine squared theta equals 3. R squared is x squared plus y squared. Now this right here we can write as 2 times r sine theta quantity squared, right? It's r squared times sine squared, which is r sine times r sine, right? Well, r sine is y, so we end up getting y squared. So this is x squared plus y squared minus 2 y squared equals 3. Y squared minus 2y squared is negative 1y squared. And we're done. So we actually get, this is a hyperbola. Okay. And then the last one here. Example 7. X squared plus y squared minus 2x equals 3. We want to convert those to polar coordinates, right? R's and thetas. Well, we know that x squared plus y squared is r squared. You might say, well, how do we know that? Well, the square root of x squared plus y squared equals r. So if you square both sides, then you get r squared equals x squared plus x. R squared equals x squared plus y squared. So this is r squared minus 2 times x, which is r cosine of theta, equals 3. And we're done. Nothing else to really simplify there. So we're done. And we are done with 6.5. That was the last lesson of the year. It means my job is done. I don't have to do anything ever again. So, anyways, last thing. Today in class, Landon Romero, Land Rover, wanted a shout out on YouTube. So, Landon, shout out.